Very good morning, friends. So welcome back to the video lecture. So we have started already the asymmetric synthesis, the introductory part of the concept asymmetric synthesis, and the next one is the chiral pool that we have already discussed yesterday. This is actually a new topic, new concept which is widely used worldwide in the field of organic chemistry, in the field of synthetic organic chemistry. And once you have a basic idea of how to synthesize this chiral compounds having enantiomerically pure chiral centers, okay, from the chiral pool strategy, okay, then you can plan synthesis of that compounds which are having chiral centers, okay, and that chiral centers are having 100% pure, or the enantiomeric excess of such compounds is high. Now today we are going to see a new concept that is known as chiral auxiliary. So yesterday we have seen a new concept, that is the chiral pool, and for chiral pool we have to use the enantiomerically pure, naturally available, cheapest, easily available sources of the starting materials which are enantiomerically pure, that are obtained from the natures, and these are generally from amino acids and sugars, that are carbohydrates, okay. Now the next concept is chiral auxiliaries. Now what is meant by chiral auxiliary, that we will see, or that we will learn by considering this example, okay. So consider a general example, general reaction of Diels-Alder reaction, that is nothing but one of the type of pericyclic reactions that you have learned in last semester. Diels-Alder reaction is a cycloaddition reaction between a diene and a dienophile, okay. So diene is the diene must be a conjugated diene. So there are two carbon-carbon double bonds are there, and a dienophile is there. Dienophile is a simple alkene. So we can write a Diels-Alder reaction, simple Diels-Alder reaction like this. So this is 1,3-butadiene plus this is ethylene, okay. So 1,3-butadiene reacts with ethylene in presence of Lewis acid catalyst. There is a formation of a cyclohexene ring, okay. So a very simple reaction can be possible here, okay. So there is a movement of electrons in cyclic manner takes place, and that's why this reaction is called as a cycloaddition reaction, okay. So we are not going to see details about this Diels-Alder reaction, but as a point of reference I am showing only you what is meant by Diels-Alder reaction. So okay, so this is one of the type of Diels-Alder reaction shown here in this example. So this is what acrylyl chloride is there, CH2 double bond CH COCl, acrylyl chloride is there, okay. And if we react this acrylyl chloride with benzyl alcohol, so this is acid chloride, and acid chloride reacts with benzyl alcohol, there is a formation of ester. So this ester is formed COO benzyl group is CH2PH group, okay. So this ester moiety is there, but our focus is on the carbon-carbon double bond, and there is only one carbon-carbon double bond. So in this Diels-Alder reaction, this moiety or this molecule will act as a dienophile, and this dienophile is achiral. There is no any chiral center present in this molecule, so that's why this dienophile will act as a achiral dienophile. Now when we treat, or when we react this achiral dienophile with achiral diene, this diene is a cyclopentadiene molecule. When reacts with this achiral dienophile, then there is a chance of formation of two products, and these two products are diastereomers of each other, okay. So when you go in detail the stereochemistry of the formation of Diels-Alder reaction products, then you can judge or you can imagine how these products are forming. Okay, so in this case I am showing only the products. Okay, so this is a dinophile, this is a dine, and this dine has a top face and bottom face. Now as this dinophile and dine both are achiral, there is a formation of two products, and the chances or the percentage of formation of these two diastereomers are 1:1. That is 50% formation of this product plus 50% formation of this product. The reaction is going to happen in very simple manner. This dine will act as, that I have already shown here, will act as dine. A cycloaddition takes place and there is a formation of 6-membered ring. So 1, 2, 3, 4. This 1, 2, 3, 4. These 4 carbon atoms are from this cyclopentadiene, and this methylene group is pointed above the plane of the molecule. Okay, so this 1, 2, 3, 4 carbon atoms are from these 1, 2, 3, 4 carbon atoms of the dine, and these 2 carbon atoms are from the carbon-carbon double bond. Okay, and there is a formation of one new carbon-carbon double bond between the product in the product. Okay, and the only difference between this and this product is the orientation of the dine when it is coming close to the dine, how it is oriented in the space, how it will be oriented in the space. That is the difference only, and due to that difference there are 2 chances for the formation of 2 different products, and hence in this case, in this molecule, this dine, that is CH2 double bond CH, will orient like this. The orientation of this I am showing here will be like this. Your dine will be like this. This will be your dine. Okay, this dine will be orienting will be like this, and your dinophile will orient like this. OPN. Okay, so this is a dine, cyclopentadiene, and this is a dinophile. Both are achiral. So from this orientation, okay, then there is a formation of this 6-membered ring. 1, 2, 3, 4, 5, 6. 6-membered ring is this. Okay, so this is the, we can say, an transition state between this dinophile and dine. Okay, and this transition state results into the formation of this product, whereas this product will form by this transition state like this. Like this, and the orientation will be like this. OPN. Okay, only the difference of orientation of this dinophile is different. Okay, so this is the difference, and that's why this orientation results into the formation of this product, where attachment of this dine or this carbonyl group is, both are endo product, no doubt, but still the attachment of this carbonyl group to this cyclic ring is at different carbon atoms. So that's why these 2 products are formed when we are reacting achiral dinophile with the achiral dine, and there is a formation of 50:50. That is a racemic mixture is formed. There is a mixture of diastereomers is formed, and that's why such molecules are very difficult to separate, and they are of no any synthetic use for the chemist. Okay, so that's why such compounds are going to form the useless or not useful products, and that's why if we have to control, if we are going to synthesize a product of Diels-Alder reaction which is going to deliver only one type of product, and that can be possible using the new concept that is known as chiral auxiliary. Now what is this chiral auxiliary? As here, due to the top phase attack of this dinophile on this dine, there is a formation of 2 endo products. this one and this one. Sorry, as there is no any chirality present in this dinophile, there are two chances the dinophile can orient either this or like this. Okay, so that's why two diastereomers can be possible. Now if we use such a dinophile, if it is chiral dinophile, if it is chiral, or if we are using a dinophile which has a chiral moiety incorporated in between the dinophile. Okay, means we have a specific dinophile and a chiral molecule is get introduced, it gets embedded into that dinophile, and due to this chiral moiety embedded into the dinophile, the stereochemistry of that dinophile is defined. Okay, stereochemistry is now specific, means specific groups have been attached to that dinophile on one side. So that's why one side of that dinophile will be, let us say, sterically hindered, crowded, and that's why from that side the attack of dyne will be not possible, and hence only one side of dinophile is available for the attack of dyne on that dinophile, and hence we are getting a product which is enantiomerically pure product, and that's why in such case there is no formation of 50:50 proportion of two diastereomers. Okay, and that's why we are getting enantiomerically pure product. Okay, so that's why a new concept that is introduced, and that concept is known as chiral auxiliary. Now what is this chiral auxiliary? Now let us see here. This is an example of chiral auxiliary, and from this example we can easily understand the meaning of chiral auxiliary. So I have taken the same molecule, that is acrylyl chloride. So this is acid chloride COCl, moiety is there. Now what I have done here, instead of reacting this acrylyl chloride directly with benzyl alcohol to form this achiral dinophile, I have used here enantiomerically pure compound. This enantiomerically pure compound which is obtained from S-valine. S-valine is the amino acid naturally available, readily available, which is a cheaper source of the cheaper source from the chiral pool. Okay, so I have made this chiral auxiliary or this chiral molecule, okay, from the S-valine amino acids. And as there is one chiral center present in this molecule which is enantiomerically pure, because it is derived from the enantiomerically pure S-valine, and that's why it is also enantiomerically pure. It is 100% pure. No other isomer is present in this molecule. Okay, so this molecule, this moiety, I am using this reagent, let us say, or auxiliary for the reaction with this acrylyl chloride. Now there is a presence of acidic proton on nitrogen atom, so I am using a base sodium hydride. So this sodium hydride is abstracting this proton, converting this NH to N minus. So nitrogen nucleophile will be generated, N minus, and this N minus will attack on this carbonyl. HCl will be knocked out, okay, and there is a direct bonding between nitrogen and this carbonyl. So amide bond will be formed here. Okay, now this is my dinophile. There is no any carbon-carbon double bond in this molecule. So that's why I am getting a single enantiomer. I am getting here a single enantiomer of the dinophile. Now you can compare the both dinophiles are in front of you on the board. This is a chiral dinophile. This is single enantiomer of dinophile. This dinophile is having chirality embedded. Chirality is embedded in the molecule of dinophile due to the attachment of this chiral auxiliary. So this molecule is chiral, and this chiral auxiliary is embedded, or it is introduced into the dinophile. So that's why now I have a chiral dinophile, and which is 100% pure. No any other enantiomer, okay, is possible, or it is present in this molecule. Okay, now this, see the structure of this dinophile. Okay, when you are looking carefully this dinophile, then you can easily observe that one of the side of this dinophile is having steric hindrance, and only one side of this dinophile having less crowding. Okay, so there is no any crowding at all on one side. So that's why such dienophile can orient in the space when it is coming across to the diene. Okay, this diene is same, that is cyclopentadiene molecule, and this reaction is taking place in presence of Levy's acid, that is diethyl aluminum chloride. Only top phase attack is possible. Only top phase attack is possible. So that's why I am getting here this product only. So due to the top phase attack, like this. Okay. Now I will explain how that happen later on. So due to the top phase attack of this dienophile on this diene, this product is only possible. There is attachment of this carbonyl group on this carbon atom. No any this carbon atom is not attached to this carbon atom of the ring like this one. Okay, so it is looking or it is resembling like this molecule. Okay, but what is additional here in this molecule? Carbonyl is next to this chiral auxiliary. So this chiral auxiliary limits the attack of this diene on one side. Only top phase attack is possible of this diene. So that's why only one enantiomer is possible. Formation of only one enantiomer is possible in this case. There is no any formation of such type of product like this, and so that's why once our work is done, once our product is obtained, we can easily remove this chiral auxiliary. Because our target molecule is this. Our target molecule is this one, not this one. So now what is our next target? Remove this chiral auxiliary. So by simple reaction with this nucleophile lithium LiOBn. Okay, so this LiOBn is existing as a Li plus OBn minus, and this OBn minus is nothing but alkoxy group Li plus OCH2PH. This is Bn, benzyl group. Okay, minus, and this O minus will attack on this carbonyl group. Okay, and this carbon nitrogen bond, amide bond will break now, and there is a formation of a new bond, that is carbonyl oxygen bond. Carbonyl oxygen bond will be there, and this is the single enantiomer as a major product that is predominantly obtained in our reaction. Okay, so that's why this is the strategy that we are applying for the synthesis of enantiomerically pure single enantiomer where we are obtaining a single enantiomer of that product. Okay, means we are getting only this type of product. Okay, it is 100% pure. This percent is not, I am concerning with the it is not concerned with the yield. Okay, mind well, this is concerning with the enantiomeric purity. Means only this product is possible, not this product is possible here. So that's why only single enantiomer we can synthesize by using this chiral auxiliary strategy. Okay, now dear friends, this is the concept of chiral auxiliary. Now what we what we can learn from these two examples? So chiral auxiliary, this is the concept in asymmetric synthesis, that is by using such chiral auxiliary. The chiral auxiliary we have used here is this, and this chiral auxiliary can be prepared from the easily available natural chiral molecule, that is from chiral pool, that is amino acids, and we have prepared this molecule from S-valine. S-valine is the amino acid which is 100% pure, and from this S-valine we have prepared this chiral auxiliary, and due to this, by the use of this chiral auxiliary, when we react this chiral auxiliary with our dienophile, there is a formation of chiral dienophile. Chiral dienophile has been prepared, and due to this chiral dienophile, the reagent attacks to the diene in a specific manner. The one side of this dienophile is sterically hindered, so the attack of diene is possible from only one direction. So that's why only one type of product can be obtained. Okay, so this chiral auxiliary is used only What is the use of this? It is used only for the introduction of a chirality, introduction of chirality into the molecule, introduction of chirality in this molecule, and once we achieve our goal, that is formation of only one single product by the stereochemical evidences, by the stereochemical knowledge, okay, then we can easily remove that chiral auxiliary from the reaction, from the molecule, okay, and we are getting our target molecule, okay, and hence again this chiral auxiliary can be recycled in the reaction mechanism. So that's why this is the concept of chiral auxiliary, and by the use of this chiral auxiliary concept, we can introduce or we can embed the chirality into the molecule, and hence we get enantiomerically pure single enantiomer. Instead of getting two diastereomers in this molecule, in this reaction, we are getting here only one type of reaction, only one type of product. So that's why this type of strategies using chiral auxiliaries is widely used in the synthesis that is known as asymmetric synthesis. Okay, now in the I am telling you how this is happening. I am telling you how this is happening, how this step is happening. Okay, so it is a imaginary step that is possible when dienophile reacting with diene. So with the help of this Lewis acid catalyst, diethyl aluminum chloride that reacts with shear, how that diastereoselective reaction can be possible. Okay, so we have COO 5-member ring with alpha isopropyl group, okay, and when it reacts with Et2AlCl, that is diethyl aluminum chloride, there is a formation of transition state between these two, and this will be like this. Aluminum at the center, okay, Et2, okay, and O alpha isopropyl group, okay. Such transition state can be possible here, okay, then which is then reacts with the diene, that is dienophile. So dienophile will attack like this, okay. So reaction will be taken place like this. Okay, cyclic rotation of these pi bonds or pi electrons will be takes place, and the orientation of this diene and dienophile will be like this. N COO isopropyl group. Okay, so the orientation will be like this, and that's why we are getting here the attack will be like this. This is, I am explaining only how that orientation of that product will be possible and how that product is obtaining. Okay, so this is top phase attack due to this blockage of this isopropyl group which is at alpha to this chiral auxiliary. Okay, this attack is possible, and we are getting here CON and all this chiral auxiliary. Okay, and then by doing reaction with LiOBN, we are breaking this bond, and finally we are getting the product which is having the OCOOBN. This is our final product. So this is the explanation of how that product is formed, or how that why it is favorable, or how that top phase attack of this dienophile takes place here. Okay, so this side is blocked due to the chiral auxiliary. Okay, so that's why this attack is possible only, and hence we are getting only this type of product, and only deprotection or breaking of this amide bond by LiOBN, we are getting the final product. Okay, so this is the explanation of Diels-Alder reaction using chiral auxiliary, which is derived from the S-valine amino acid, and S-valine is the naturally available amino acid. Okay, thank you. So next one is the next reaction under this is chiral auxiliary is the, for your detailed understanding, consider another example. we are going to see the another Diels-Alder reaction. See here, NHCOO, this C, here now it is phenyl ring, and here it is methyl group. Okay, so this chiral auxiliary is looking like the same. The structure of this chiral auxiliary is looking like it is just similar to that of the chiral auxiliary obtained from the S-valine. Okay, but the substituents attached to this 5-membered ring are different. Here it is phenyl, and here it is methyl group. Okay, in the previous example, this carbon atom doesn't have any substituent, and this carbon atom had isopropyl group. Okay, and this chiral auxiliary have been prepared from ephedrine. Okay, sorry, norepinephrine. This chiral auxiliary is obtained from norepinephrine derived auxiliary. This chiral auxiliary we have prepared synthetically in the laboratory, and it is obtained from the norepinephrine. Okay, now this is hydrogen here. Now when we are using sodium hydride base and same molecule, that is acrylyl chloride, what happens? This base will abstract this proton, nitrogen, negative charge on nitrogen will attack on this carbonyl. There is a formation of amide bond. A new amide bond will be formed, and it will be like this: CO there, N COO, here phenyl group, and here methyl group. Okay, here. So another type of chiral auxiliary embedded into this dienophile. We have taken this same, that is acrylic chloride, and to this we have reacted this chiral auxiliary and we are getting now this. Now this chiral auxiliary has exactly reverse orientation of this dienophile. Okay, so that's why the in this case bottom phase attack of diene will takes place on this dienophile. This dienophile is now chiral due to the introduction of this chiral auxiliary in this dienophile. Okay, and the case is exactly reverse to that of the previous one. Okay, so that's why when we react with this, when we react this with our diene, that is cyclopentadiene, all the things remaining same, only we have changed the chiral auxiliary here. Same here, diethyl aluminum chloride, Lewis acid catalyst we have used here. This is thermally allowed cycloaddition reaction, Diels-Alder reaction. Okay, and what happens here? We are getting a different product. We are getting here different product, and the product here is like this: CO, N, COO, methyl phenyl. Okay, so this type of product we are obtaining by reacting this chiral dienophile with this cyclopentadiene. Okay, and this is again we are getting as a single enantiomer. Single enantiomer, which is 100% pure. 100% pure means in this case there is no formation of product which we have obtained in the previous case. Only this type of product is possible. Okay, and only the remaining thing, the next step is same, that is using LiOBn. This amide bond will be broken, and you are getting our desired molecule COOBn. Okay, so predominantly we are getting enantiomerically pure this type of adduct in the cycloaddition Diels-Alder reaction between this dienophile and this cyclopentadiene. Okay, so this is the use of chiral auxiliaries. Again, the concept is same here, applicable to both. Okay, that is we have derived this chiral auxiliary from the norepinephrine. Okay, norepinephrine is a natural product. Okay, and so that's why by using this, the achiral dienophile is converted to chiral dienophile. One side of the one face of the dienophile is now blocked, and that's why only bottom face attack of this diene is possible, and hence we are getting only one product which is enantiomerically pure. Okay, and by simple deprotection we can remove this chiral auxiliary and finally getting the target molecule. So this is the concept of chiral auxiliary. Okay, now consider as one more example of this chiral dienophile derived from the S polygon. Okay, the next example of this chiral dienophile that is derived from the S dilephone, that we will discuss now. So S polygon is there. S polygon. Okay, so this is carbon carbon double bond, here this carbon atom one, two, three, 4, 5, 6. Okay, let it be carbon carbon double bond, iso dimethyl functionality is there. Okay, so this is S polygon. This S polygon is naturally available molecule, and by doing some chemical steps, chemical reactions on this S polygon, we can convert it into this molecule, that is hydroxy here, that is reduction of this carbonyl group and converting this side chain into dimethylphenyl group. Dimethylphenyl group, again here methyl group as it is. So this is, what is this? 8-phenyl menthol. 8-phenyl menthol. Now when this 8-phenyl menthol reacts with same, that is acrylyl chloride. Okay, so by using base, the base will abstract this acidic proton. There is a formation of O minus, and this O minus will attack on this carbonyl group. Cl will be leaving group, and there is a formation of ester, that is OCO linkage will be there. Okay, and the structure will be like this. Dimethylphenyl, then O, here methyl group as it is, OCO. Okay, so in this case this chiral dienophile is prepared. Chiral dienophile has been prepared. Okay, and this chiral dienophile is used in the synthesis of prostaglandin. Like this. So we have this chiral dienophile, and when this chiral dienophile reacts with, I am writing directly here, the dienophile in this case is this is nothing but I am writing simple structure. Cyclopentadiene molecule is there, and to this CS2 there is one more CS2OBN. Okay, so this ether linkage is there to this diene. This cyclopentadiene will act as diene, and this carbon-carbon double bond is act as dienophile. There is a reaction between this achiral diene and this is chiral dienophile. Okay, so this chiral dienophile, again due to the use of this chiral auxiliary, this molecule is converted to chiral dienophile, and that's why it is again giving our target molecule, that is prostaglandin, and the stereochemistry of that prostaglandin is again fixed due to this chiral auxiliary, and the structure of product is like this. This is CS2, this is CH group, and this CS2OBN group will be as it is, and this carbon atom is now having CO2R. So R means this all, chiral auxiliary group, R group. Okay, I am writing in short R group. Okay, so due to this chiral auxiliary, the stereochemistry is controlled here, and we are getting only one enantiomer which is enantiomerically pure, and only one enantiomer is formed. So that's why this is the use of chiral auxiliary in the concept of asymmetric synthesis. Okay, so I think you got it properly. Kindly see this video number of times, then you can understand easily the concept of chiral auxiliary. Okay, thank you very much. Have a nice day.